Welcome to the student ePoster pitch competition. This is the first time that we've done this ePoster pitch at the Plant Protein Science and Technology Forum. And we're looking forward to the 3 finalists. And we want to thank all the students for sending wonderful abstracts. It was difficult to pick the finalists. And we wish our finalists the best. Here's what's going to happen, and I want to get this going. Each of the 3 finalists will present their talk for up to 5 minutes. They're going to use a visual aid, but they're not going to actually redo their poster. Please go to the website to see their posters. After each student presents, there will be a 5-minute Q&A with the judges for that specific poster. And please, the audience is free to post your questions at that time on the website. After all the 3 presentations have ended, we'll bring all the finalists and judges back for a final group Q&A. And at that time, we're gonna open up the poll to the audience. So please vote for your favorite pitch, because that will count towards the final score. And finally, we'll announce the final winners after Dr. Phil Krul will close the session up, and after he's done, we will announce the winners when the scores are tallied. So let's get started with the first speaker. The first presenter is Gulkirpik. She's a PhD candidate in food science at the University of Illinois at Urbana, Champaign. She received her bachelor's degree in food engineering at Istanbul Technical University in 2017. Her doctoral research focuses on developing and evaluating process technologies to improve the utilization of soybean products and enhance the nutritional value of complementary foods in low resource settings. Her presentation will be evaluation of a low-cost soy protein concentrate production method. Good luck, AJ.
Thank you so much, Dr. Krul. Let me share my screen quickly. Okay. There you go. All right. Thank you very much again, Dr. Krul, and thanks everyone for being here with us today. My name is Agri-Food. I am a PhD candidate in food science at the University of Illinois at Urbana, Champaign, and it's my pleasure to present our research on behalf of our team today. Did you know that every country in the world is affected from malnutrition? It is a global issue in which at least one of the forms of it is existing in every country. In some regions, it's more severe than the others, like in Africa. One of the most common forms of malnutrition seen in children is stunting, which refers to a child who is too short for his or her age. While undernutrition has been declining in many regions, Africa is the only region where the number of stunted kids has increased. For most of part, the stunting in Africa is associated with the poverty, as well as a limited access and availability of high protein and nutrient-dense foods and specific minerals. As a member of Soybean Innovation Lab, which is a research and development USAID funded program, we argue that soybeans can be an alternative source of protein for children in sub-Saharan Africa. However, there are some hurdles with their utilization for human consumption. Most of the soybeans are produced for their oil content, which can be extracted either by using mechanical forces like pressing or chemical treatments such as solvent extraction. In this process, in addition to the oil, defatted or low-fat soy cake is also obtained, which is then either dried and sold for animal feed or further processed to produce soy protein products for human consumption, such as soy protein concentrate. Despite its rich nutrient composition, the utilization of defatted or low-fat soy cake for producing soy protein concentrate is quite limited in this context due to the inadequate processing capabilities, high processing costs, and the complexity of the advance of the current processing technologies. Additionally, the soy cake is very stable when it is obtained after a solvent extraction process. However, in the sub-Saharan Africa, it is mainly processed by mechanical expellers, leaving a significant amount of oil behind in the cake and making it less stable and causing processors less likely to use and produce this product. In the Soybean Innovation Lab, last few years, our focus has been enhancing the utilization of raw materials by improving their stability and maximizing the nutrition utilization. Today, I'm going to tell you one example in which we're looking at a low resource method to enhance the utilization of the soy protein cake coming after the oil extraction process by reducing the cost of the processing and maximizing the stability of the materials that we produce. This flowchart in here is illustrating the steps of this technique. It begins with the mixing the starting materials with water, then the soy flour water mixture is centrifuged for separation, and after centrifugation, the supernatants are decanted, the precipitated wet soy protein concentrates are separated, dried, and finally ground into powder. In this study, in addition to the defatted and defatted toasted soy flours, we used two types of extruded expelled soy flours that still contained significant amount of oil. One had 7.6% and the other one had almost 13%. We evaluated the effect of different mixing times and temperatures on the protein content of produced SPC samples, and we also measured the protein, oil, and phytic acid contents of both flour samples and the SPC materials made from them. Our findings show that mixing time and temperature did not significantly affect the protein content of the produced SPC materials. I will now show you 3 graphs for the outcomes we evaluated. And the first one is for the protein content. In this graph and the next ones, the lighter green bars are representing the materials before processing, and the darker green bars are presenting the SPC materials made from them. The first set of bars is for defatted samples, the second is for defatted toasted, the third is for the low-fat soy flour with 7.6% oil, and the last set is for the low-fat with the 12.8% oil. All these samples went through the same process, and as you can see, the accumulation of protein went up to 63% with the extruded expelled samples. Next graph, I will show you the oil content, and you can see that the samples had more oil, of course had a higher reduction after the processing, and this decrease was more than 45%. Finally, in the last graph, you are seeing the phytic acid contents of the samples, and in which all the samples across the board were reduced more than 55%. So can we produce soy protein concentrate with using less resources? This study showed that yes, we can definitely do that. With this alternative, less resource demanding method, we can produce SPC with a protein content more than 60% and with lower oil and phytic acid content from the defatted or low-fat soy flour using locally available materials and equipment. This reduction in oil can also be associated with higher stability, and our current studies are focusing on enhancing the scalability of this technique and evaluating the stability of the produced SPC materials under the accelerated conditions. With this alternative method, the utilization of soy protein concentrate for human consumption can be improved, and we can also boost the nutrition of vulnerable populations. Thank you.
Well, thank you very much, AJ, for that presentation. And we now have about 5 minutes or so for questions from the judges. That was a very clear presentation and right on time. So perfect.
Thank you so much.
Any of the other judges want to pipe in or?
Sure, it's Jim House here, University of Manitoba. Very nice presentation. I wonder if you could comment on the nutritional properties of your product. In particular, I'm thinking about the digestibility of the protein or the amino acid composition. Do you have any evidence as to how this low resource method might impact the protein quality of the sample that you're evaluating?
Definitely. Thank you very much. It's a great question, Dr. House. So in this case, this project is for the lab scale production. So our next step is to characterize our final product, and we will be definitely looking into the digestibility, especially for the protein and the starch as well. So one of the things that we so far evaluated was the antinutrients and the protein and oil contents. Antinutrients was also has an impact on digestibility of the nutrients as well. So that was the initial test that we applied, but once we figure out the larger scale production of this material, we will do the full characterization, the nutritional profile of this material as well.
Great, thank you very much.
You're welcome, thank you. Yes, next question, please. Thank you.
Janitha?
Nice presentation, EJ.
Thank you.
My question is, so still there is some oil content remaining in the protein concentrate, right?
Mm-hmm.
So did you do any stability test, or how is the stability of these protein concentrates?
Yes, definitely. Great question. So we actually started working on this question. The next step that we were planning to do is this accelerated condition study to understand how the oxidative stability of this product under the high temperatures and humidity conditions. And we will be exploring the changes in the oxidative stability markers to understand their stability. We actually, the first thing that we have done after we produced this material was to measure the second products of the oxidation with using the T-bars analysis. And our initial results show that the SPC materials significantly had less oxidized than the raw materials. However, to be for sure understand that it's more stable, we need to do a larger study with this accelerated conditions to understand how their oxidative stability will change under these certain conditions.
Okay, thank you.
You're welcome. Thank you.
Okay. Chris, you have a question?
Yes, great presentation. Chris Martinangeli from Pulse Canada. Just wondering if you tested or have evaluated the functionality of your product in food platforms. Are there any concerns around optimized inclusion rates or performance in certain platforms as you aim to use this to address some of the malnutritional aspects in the developing world?
Definitely. Great question. Thank you so much again. So yes, we wanted to turn this product into a ingredient that we can incorporate it in various types of foods, especially maybe for the snacks and like beverages or other types of maybe complementary foods as well. So definitely once we have the finalized product at the end, we will be testing its performances in different types of foods. For now, we're mirroring the study in Uganda to scale up and produce it in larger scales. And our colleagues in Uganda has been trying to use this in various types of foods, such as breads and everything. But we haven't tested any functional tests yet in the product like right now, the one that we tested in the lab scale. Once we have the finalized like large scale product at the end, we will be having all the characterization of this product.
Thank you.
Thank you.
And I'll just one last question before our time will be up. Are you using soybeans that are locally produced, or are these beans that are from the North America?
No, these are the products like, yes, have been used in the found in the sub-Saharan Africa. So we are totally using the locally available materials and equipment so that we can adapt this technology to produce soy protein concentrate in the conditions of in the context of sub-Saharan Africa. And again, we're mirroring this technology over there too with our colleagues. They have been using their own equipments as well and using the same materials and equipments to produce this product.
Perfect. Thank you very much.
Thank you so much.
Okay, so I thank you very much, AJ, for that. And we're going to take a little pause so that the next speaker can get her slides and ready for her presentation. Thank you very much again. Okay, our second finalist is Nadia Grasso, and she is a PhD candidate in food science working under the supervision of Dr. Seamus O'Mahony in the Food Ingredients Research Group at the University of College Cork in Ireland. Nadia is in her third year of her PhD, and her project is about the formulation and processing of sustainable and nutritious plant-based dairy alternative products. Nadia will present today on the influence of protein concentration on key quality attributes of chickpea-based alternatives to cheese. Good luck, Nadia. Thank you.
Thank you very much for the introduction, and hello everyone. Today I'm very glad to share with all of you our work conducting the Food Ingredients Research Group. But first of all, a bit of background. As we all know, the global population is expected to reach almost 10 billion people by 2050. And to feed such a large global population sustainably represents a big challenge. In this scenario, animal-based systems are major contributors to climate change and in turn biodiversity loss, being a resource-intensive protein source. This, together with increasing consumer awareness of animal welfare and the impact of animal food on health, is driving growth in the development of plant-based alternatives to animal-based products, such as cheese, which represents the plant-based product category with the highest potential demand for those following a plant-based diet or reducing their consumption of animal products. On the other hand, most commercially available cheese alternatives rely on starch and coconut oil to build structure and mimic dairy proteins and fat, thus having a low protein and high saturated fat content, which make them nutritionally inferior to traditional cheese. Therefore, to formulate plant-based cheese alternatives with improved nutritional profile and low environmental impact, researchers are currently investigating plant protein ingredients. However, dairy protein provides cheese products with unique sensory and texture, and to replicate such properties using plant proteins can be challenging. Due to their nutritional value and functionality, chickpea protein ingredients show great potential in the development of new and reformulated food products. In our work, we determine the influence of protein concentration on chickpea-based alternatives to cheese and the age-induced effects on 1-month-old samples in terms of key quality attributes. To formulate our 4 prototypes with increasing protein and decreasing carbohydrates content, we used different ratios of chickpea flour and chickpea protein concentrate. We blended these with shea butter and water with lactic acid to have the same fat content, pH, and moisture for all samples. In terms of results, the thermograms of the chickpea-based samples showed a main peak around 30 degrees, corresponding to transition of the shea butter ingredients, and a smaller peak around 70 degrees, related to starch gelatinization, which decreased with decreasing carbohydrates content in the samples according to the formulation. Images of the microstructure showed formation of a protein matrix and a low occurrence of black areas, representing the carbohydrate components associated with increasing protein contents. The 100 chickpea flour sample showed many black areas, indicating that the carbohydrate fractions gave structure to the sample and in turn influenced its physicochemical properties. None of the chickpea-based samples melted under the testing conditions, and the same happened after storage. Thus, improvement of the melting behavior of chickpea-based systems will be necessary for their application in the formulation of alternatives to cheese. Texture is one of the main quality features of cheese products. Here, whole samples showed increasing values of adhesiveness, springiness, and cohesiveness associated with increasing protein content, with the same trend observed after 1 month. On the other hand, hardness and firmness were the highest for the 100 chickpea flour sample, and this might be attributed to the higher starch content, which retrograded during storage. After 1 month, an increase in hardness and firmness was observed for all samples, and in particular for the 100 chickpea flour, probably due to the high levels of starch retrogradation during storage. So to sum up, as we could see, some differences linked to protein concentration were observed in the chickpea-based samples, and 1 month of storage affected mainly color and texture of the prototypes. The results of this work showed the effect of chickpea protein on quality attributes for the development of chickpea-based alternatives to cheese. Furthermore, chickpea protein ingredients showed great potential and some challenges related to the application in cheese alternative products. The use of plant proteins to formulate alternatives to animal-based products can help in tackling the environmental issues we are facing nowadays and in the future. And it is our responsibility to give our contribution to this cause. Thank you very much for your attention.
Very good.
Very good. Thank you very much. Again, right on time and in fact a little early. So we have time for questions from our judges. So I see both Jim and Chris. I'll start with Chris first.
I feel like we're on Jeopardy here. Beating to the buzzer. Great presentation. Just a question around your choice of using chickpea. Why chickpea versus some of the other ingredients out there in the plant-based space, just pea, where you see a lot of the innovation? Chickpea seems to be an interesting and novel choice in this case.
Yeah, we did. Thank you for your question. We did many preliminary trials investigating different plant proteins. And I thought of using the chickpea ingredient because it's something quite new. And in terms of flavor, seemed to perform much better compared to other plant proteins because the flavor was milder compared to, for example, pea. or even we tried different lentil, potatoes, etc. And also from a functionality point of view, seem to perform very well in this kind of application for cheese alternative products. But of course, we will try to investigate even further in the next years, different sorts of proteins.
Great, thank you.
Thank you.
Thank you, Chris. Jim?
Great. Well, thanks very much, Nadia. Excellent presentation. I just wanted to ask you a question, and this is something that we typically see in nutrition studies as well. You talked about increasing protein, but when you're looking at increasing protein, you're by definition also decreasing something else. So my question to you is, how do you know that the effects that you're seeing aren't due to a reduction in the carbohydrate content and not an increase in the protein content? Can you tease out those effects, or how would how could you address that fact?
Okay, thank you very much for your question. Actually, in our work, we tried to explain what was happening in our prototypes, both looking at the protein and the carbohydrates. So we tried to explain what was going on, especially in the texture, for example, trying to see the starch as well influence on the texture of our prototype. So we didn't focus only on the protein fraction, but also on the carbohydrate fraction. In some cases, it was quite obvious that was an influence of protein. For example, the structure, you can see clearly that is the protein matrix is increasing due to the addition of protein. But in other cases, for example, the texture, you could object that some features were related to the starch other than the protein fractions in that case.
Great, good. Thanks very much.
Thank you.
Okay, and Janitha?
Yeah, nice presentation, Nadia. It's a nice product to work with. Looks like my question is from the fat side rather than protein side. When you say the fat source you have used in your product is shea butter, so psychologically I'm more connected to, when I hear shea butter, more connected to personal care products than food products. Two questions: why shea butter, and is there anything equivalent in food grade fat that gives functionality as shea butter?
So thanks for the question. That's a very interesting point to raise. Shea butter, I chose shea butter because usually in cheese alternative products, they use coconut oil, right? So coconut oil is actually pretty high in saturated fats, but is solid at room temperature, so it gives a nice texture to the products. In my case, I tried to use the shea butter ingredient because it has the same solid nature at room temperature, but at the same time has lower saturated fats compared to coconut oil. So this allows to have a nicer nutritional profile of the final product. Actually, the ingredients that we purchase is from the Fuji oil and is already grass, so it can be used in food products. So it's safe to use in food products. And I think another nice point of the shea butter is that is way milder compared to coconut oil in terms of texture and also smell. So I think it's a nice option to investigate. In our work, we focus more on the protein, but I mean, the fat fracture is very, very interesting to study as well.
Thank you.
Thank you.
And I'll just have one last question for our time. When you're talking about cheeses, I think of all sorts of things from cream cheese to aged cheeses to very hard cheeses. What are you trying to mimic, or what are you hoping to achieve?
So thank you for the question. In this study, we tried to achieve something similar to a hard cheese, but we ended up having something more spreadable. In the study that I'm conducting now, so I'm trying to move forward, for example, fixing the issues on the meltability, and I will try to have something similar to a hard cheese, but which will be able to also melt at higher temperature. So yeah, something similar to, let's say something in the middle between a mozzarella type of cheese and a cheddar cheese. So kind of semi-hard texture. Thank you.
Okay, thank you very much, and I appreciate that. And I will go now to our next speaker. And I'm on under mute. Okay, we're just going to have a little break while the next speaker gets her slides together. Okay, our third finalist is Cäcilie Möller. She's a PhD candidate and food process engineer at Wageningen University in the Netherlands. Anna received her master's degree from the Technical University of Munich in 2018 and is about to finish her PhD. Her research comprises the development of fractionation technologies based on already proven or novel processes to create mildly refined fractions from crops. She analyzes the functional properties of these fractions as they will form the basis for novel food ingredients. The main goal of her research is to replace energy-intensive pure ingredients with less processed ingredients, their efficient processing, and a focus on target functional applications such as structure for meat analogs. Anna, good luck.
Thank you very much for the kind introduction, Dr. Krul, and thank you for the opportunity to present my research here today. In this presentation, I will show you that without the use of chemicals, we can produce highly purified protein isolates from pea. And on top of that, the proteins will still be native. Current plant protein isolates are produced with intensive processing. Flours are dispersed with ample water into slurries, and proteins are extracted with chemical adjustments, which are alkaline extraction or isoelectric precipitation, for example. And this is mainly done to obtain highly pure ingredients. This also comes at the expense of protein nativity. And therefore, our research aim was to develop a fractionation technique with which we can obtain highly pure ingredients with proteins in their native state. Our fractionation starts with dispersing pea flour in water. We found that water provides an additional driving force for mild fractionation, as it further disentangles pea flour particles. So with simple centrifugation steps, we can separate the slurry into 3 fractions. You can see here the starch-rich fraction, a soluble protein fraction, and a non-soluble protein fraction. And these fractions are still less pure than those from conventional fractionation, but the components keep their functional properties, their native functional properties. Here you can see a Grassmann diagram, which depicts a conceptual design of the entire fractionation process. Fresh water is depicted in light blue, and the pea dispersions are in dark blue. To increase the purity, we applied additional washing steps, which you can see by the addition of the water into the different streams. And we have applied ultrafiltration for the soluble protein fraction. Moreover, with adding nanofiltration at the after ultrafiltration to the watery stream, this would allow the recirculation of water of most of the water. Let's look at how the new process performed. Here we plotted the protein purity over the protein yield, and pea flour is the starting material, and at a protein purity of 21.5%, which I hope you can see here, and of course a yield of this is a bit too fast, and a yield of 100%. With conventional wet fractionation, the protein purity is increased to 76%, but the yield decreases to 80%. So now we lose 20% of the protein throughout the process. So now with our method, we achieve similar purities and a higher yield of 87%. So now we only use 13% of the protein. And what you can see is that we managed to separate pea with high efficiency using only water. In our process, the extra washing steps mainly resulted in an increase in protein yield and the purity was mainly increased by the additional ultrafiltration of the soluble protein fraction. Now, we wanted to judge on the feasibility to upscale a process, and we compared it to the whey protein isolation from dairy industry. And we calculated that the required water for both processes is around the same order of magnitude. And what we realized throughout this project is that we might be on a more of a rocky path with the conventional protein fractionation that is currently used in plant processing. So we proposed to rather look at the dairy industry. They have extensive know-how with milk separation, which is also an aqueous protein dispersion. And I think the application of these processes and their know-how to plant protein purification will result in new routes for plant ingredient production. Oh, sorry. So our research builds the basis for a continuous process for pea protein isolation. And what we propose is to use 2 decanters for protein and starch separation and a subsequent ultrafiltration for the soluble protein fraction. And this novel process uses only water to produce protein and starch isolates from yellow pea. And we think that it has big potential to be upscaled to produce more sustainable native plant-based ingredients. And with this, I would like to end, and thank you very much for your attention. And if you have any questions, I'm happy to answer.
Thank you very much. That was a nice presentation. And again, well delivered and on time. So now we'll have questions from the judges for the next 5 minutes. Chris, you have your hand up first. So you win the Jeopardy round.
Thank you. Great presentation. Just wondering if you could comment on the hedonic or sensory profile of the protein. Does it exhibit any benefits through the extraction using the water-only process versus the other processes?
Sorry, on the sensory profile?
Yeah.
Well, we haven't tested that yet. So far, well, what I can observe is more of a smell of the different fractions. And I would say that the soluble protein fraction is has the most intense smell. But I think this would for sure be, for ongoing research to investigate what did we actually extract and how can we apply it.
Thank you.
Thank you.
Janitha?
I think Jim was before me.
Oh, yeah. Oh well, that's fine. You can go ahead. He's smiling. He's
Okay. Yeah, nice presentation, Anna. My question is about particle sizes. So how much particle size reduction you need to do before extraction?
So we have, in a previous paper, we have studied how we can disentangle the pea, and what we can manage is that we go to starch granule size, and that's about 30 micrometers of size. And what we see is that we have some bigger chunks and some smaller chunks, but the addition of water actually has this additional disentanglement of the particles. So everything, I think, more or less dissolves to maximum, 30 micrometers of size of starch granules.
Good. Thanks.
Okay, Jim.
Great. Excellent presentation, Donna. Wanted to just sort of maybe follow up on what Janitha was asking you, as it relates to sort of additional green processing steps that for consideration. You started off with using the native flour, the pea flour. I'm just wondering if you've tried the process with a concentrate that has a little higher protein content to begin with, and whether or not you see similar extraction efficiencies with using a concentrate with your water-only method.
Thank you. I personally have not. It has been investigated in our group. There was a talk today by one of our professors who talked about hybrid fractionation. So this is dry fractionation followed up by mild wet fractionation. And the first step, so the dry fractionation also already results in some losses. So then if we apply the mild fractionation, the mild wet fractionation afterwards, of course, we might increase these losses. So I would propose in this process to really, start with the water immediately. But of course, the dry fractionation before might have some, might be a bit beneficial in terms of water usage. So might be that we could reduce the amount of water that's necessary.
And can I ask a quick follow-up? You've focused on yellow pea. Have you looked at other crops? For example, our previous student was looking at chickpea, which might have a little higher fat content. I'm just wondering how fat content might influence the results in this.
Yeah, that is actually an interesting question. So my first thought about chickpea would be that the starch granule size is actually different. So it performs quite different in dry fractionation. So therefore, wet fractionation might actually be, maybe more efficient to separate. In terms of the fat content, I must say that I don't really know where the fat would end up. I could imagine that it has quite an influence. In the beginning, the milling, so how small can you go with the particle size, and then also in terms of the separation. So this would need to be definitely taken into account.
Great, thanks very much.
Okay, before we run out of time, one last question. In the dairy industry, which you are looking at as a reference, they try to reuse most of the water. So is your process doing the same thing? In other words, you recoup a lot of the water and that can be reused for subsequent processing?
Yes, that is the idea. So in the first Grassmann diagram that I showed, we calculated how much water was necessary to fractionate 1 kilogram of pea flour. And that is actually around 23 kilograms. And with the process that we calculated, we could be able to recirculate 20 kilograms of the water. So quite the majority.
Wow,
so I think
great. All right, well, we're going to take a short break to get everybody back on screen, and we're going to have the group Q&A, and I encourage everybody at that point in the audience to vote for your favorite presenter. And thank you again, Anna, and we'll go to the next group Q&A. Welcome back. And again, I encourage everyone now the vote is open. Just like America's Got Talent, we've got AOCS has got great talent, and you heard from the three finalists here. We have 10 minutes now from more questions and I put your questions in the audience, and I'm going to try to capture those, and our judges will continue to ask questions of the finalists. Go ahead. Anybody have a question? I'm going to start collecting these. Okay, I'm going to ask a question for AJ from, no, that's not for AJ. Okay, for Nadia. No, this is for AJ. Is this appropriate for school feeding in sub-Saharan Africa in the process that and the product that you're generating?
Jay, I think you need to turn your microphone on.
Oh, I'm sorry. Can you hear me right now?
Yeah.
Yes, we can.
Okay, I'm sorry about that. Yeah, thank you very much for the question. It's actually one of the focus areas that we have been working on as a soybean innovation lab human nutrition team. So one of the things that we want to address is the school lunch programs, school feeding programs, and this material that we're developing. Right now it's in the lab scale, but once it's in the full scale, we will definitely be considering making it available for the school lunch programs.
Great, great.
Thank you.
Okay, and I don't see any other questions that are burning from the audience. So I go to the judges, Jim or Chris or Janitha.
Oh, sure, I can ask a question. Maybe one to Nadia. Maybe just to follow up on my other questions about sort of that protein to carbohydrate ratio. Do you think that carbohydrate quality would influence your results if you looked at sort of the distribution of the fiber component versus the starch component? Do you think that would have an impact on your results?
Thank you for the question. Yeah, it for sure it does. And we actually did first on the ingredients, we did a starch method, the Megazyme kit, to assess the amount of starch that was in the chickpea flour and the protein concentrate. And we've seen that the chickpea flour has higher amount of starch compared to the chickpea protein concentrate. And in that case, of course, the starch has a lot of influence on the 100 chickpea flour sample, which was just chickpea flour, so no protein concentrate. While on the other hand, probably the fiber has more impact on the texture and the functionality of the ingredients compared to the starch. So yeah, for sure.
Great, thanks very much for that answer.
Thank you.
Yeah.
Yeah. I have a question for Anna and then Nadia. Anna, in your process, starch fraction, I understand that goes to the solid fraction, right? Starch. How about starch enrichment in there, and as well as the fiber content in that fraction?
Yes, thank you for your question. So we see starch enrichment with the washing steps. We go actually from around 78% to 97% of starch content in that fraction. Now that might be, yeah, that might be true. Around that, but we go to more than 90% starch content in that fraction. And for fibers, I think they end up more in the soluble and non-soluble protein fraction. So soluble and non-soluble carbohydrates respectively, because the first step where we separate the starch is really short. So I think only the starch granules that are just bigger and heavier really sediment.
Okay, right. For Nadia, so you looked at mostly the physical characteristics of cheese, the melting characteristics and color as well, right? We all know the flavor is the one that cheese, everybody likes that. How you intend to get the flavor? Are you planning to going through any other biological transformation or just adding anything?
Thank you for the question. Flavor, well, of course, it's a very important feature. We will of course, do some research on that in the later stage of my PhD project. And we were thinking, well, there are many methods that we could try to improve flavor of this kind of products. One of these can be fermentation, which for sure will change totally the flavor profile of the product. Otherwise, we were thinking also of trying maybe flavorings that now you can find easily from the like to purchase and insert in our formulation. So yeah, we will investigate the flavor profiles, but in the later stage when we will first solve the issues on the texture and meltability, that these are the main things to address, let's say.
Okay, good. Thank you both.
Oh, Jim has another question.
Thanks, Elaine. Yeah, the question for AJ. I wanted to just ask you a little bit about the microbial safety of your product. You've got soybeans that are originating from sub-Saharan Africa. You're going through a wet process and then you're drying it. Have you looked at the the potential for microorganisms to be developing through this process? I'm wondering if you can comment on the safety of the process from a microbial standpoint.
Yeah, definitely. Thank you very much for the question, Dr. House. So we haven't conducted any microbiological tests in the final product yet, but the drying process that we are applying, we're targeting the moisture content to decrease below 10%, which is helping us to create a little bit like food safety over there. But however, to make sure that it is 100% food safe, we need to conduct a comprehensive microbiological testing so that I can tell you that it is free from the microorganisms and pathogens. However, the drying process in this case is helping us to decrease the moisture content so that the kind of eliminating us to prevent microbial growth, I would say.
I might also recommend looking at some of the endemic mycotoxins and
definitely
fungi that might be present within that region as well.
Definitely.
Thanks very much.
Thank you very much for the question.
Okay, and I think we're almost at the end of the questions. I have one for Anna. When you're using your ultrafiltration and nanofiltration, are you able to use your membrane, since that's a fairly expensive step? Is that something that gets clogged up readily, or you have it like ceramic membranes or something that's relatively easy to clean?
So what we've done there is also, taken a look more towards dairy industry and whey protein isolation. They use a lot of dia water, so they kind of constantly clean off or redilute the stream, and that way we stay at a dry matter content of around 10%, and that helps the membrane filtration quite a bit.
Okay, great. If there are no more questions, Chris or anybody, Chris,
I had one question.
Yeah.
Sorry, you didn't see my hand. I took it down in terms
you took
of
it down.
time,
Okay,
with
sorry.
respect to time. But just a quick question, I guess all three candidates can jump in. Just wondering, some of the data that you presented and the process you presented could be perceived as fairly new. Just wondering if you're aware of any regulatory challenges in jurisdictions with respect to perhaps adopting some of these technologies within the food systems within specific jurisdictions. Would they be considered novel processes, for example? And
all three of you can just do a short response to that.
I can go first if that's okay.
Yeah.
So yeah, actually we have just applied for a patent disclosure for the method that we have developed for this SPC material, the low-cost method that we're applying. This is definitely very applicable for if you consider the context of sub-Saharan Africa, and it's unique when you consider because it's using water only as a solvent, and it's eliminating the solventizing step in this case, and it is giving you the advantage to work with the defatted or low-fat soy cake to turn it into a soy protein product, which is the utilization of it very limited in the sub-Saharan Africa. So definitely it's an innovative process, I would say. Thank you so much.
Okay, Anna?
Yes, I would say, so we are about to publish a paper on this process, open access. So I guess that's going to be available. No restrictions there. And then I think in regard of P, that's already widely applied all over the world. So I would also say that there are not really restrictions there, and maybe more towards in terms of digestibility and functional properties. There needs to be a bit more research on how the fractions perform in the end, but that can, I think, all be done. Thank you.
Okay, Nadia?
Yeah, well, for us, the process is very easy and straightforward since we're just using a Thermomix, which is pretty common for food industry on preliminary trials. And then, of course, it would be a matter of transferring this to large scale, but I don't see issues there. And as Anna just said, the only thing will be just assuring that the digestibility of the protein ingredients will be good enough to be sold on the market, just that.
All right. Well, I thank you again for your wonderful participation, and everyone responded to all the questions very well. So we're going to take a break and have Phil present. And when I come back, we'll be announcing the winners. Thank you very much again. And we'll take a break to fill now. Thank you.
Fantastic. Okay, guys, I'm gonna share my screen here. How's that? Is that it? Okay. Are we live yet? Okay. Thanks, everybody. Wow, what three great finalists for the student ePoster. So I will not tarry because we want to see what the final votes are. They're all terrific. Great to see the industry and the society in such great hands, and fantastic to see the research as well too. We have a colleague who is going to be speaking right after this, Dr. Scott Bloomer, who I mentioned in my opening on Tuesday as a director of tech services for AOCS. Scott is also a champion of lab proficiency across the entire portfolio of methods that AOCS supports, and all the industry and commercial activities that those allow. And as we launched into this this initiative and this priority for AOCS, and as the industry around plants and alternative proteins has exploded, the awareness that many of us had for quite some time about the lack of standardized methods started to get higher and higher and higher. And so Scott has begun a process where he's trying to put together an expert group that would have common interest in this space, much like the long history of American Oil Chemists Society started with a bunch of cotton oil chemists more than a century ago to try to develop common standardized methods that would allow the cotton industry to grow and flourish. We're at a point in time where the plant protein and alternative protein industry really is crying out for that as well too. So I'm here in Scott's stead to make the pitch to those in the audience around the world who have a passion for this and recognize the same kind of challenge, in hopes that they would come forward and participate. Some of these might be in analytical service providing settings, people in industry who are working in these fields who would like to see a commonality and adoption of methods that would help the commercial and regulatory activities that we all know will be critically important as we go forward. Well, just so happens that we actually have a poster from student Annalise Goins at Cal State University in Fresno. And I show the abstract from her poster today, and I'll show you actually her image of her poster along with her mentor at Cal State. This is exactly what Annalise has delved into. She's seen the same issue as well too, and is working down this path. So we use it as an illustration of the kinds of things that ultimately we know we face, but it helps dimensionalize it. Let me go one more here. There we go. So here's Annalise and Sarah's ePoster. We won't go into the details. It's both visually rich and data rich, but essentially they've tried to go into the literature and look at a survey of a number of the methods for what are thought to be fairly standard functionality methodologies to be used on various materials with proteinaceous materials in particular. Things like emulsification, water absorption, gelation, solubility, et cetera, et cetera. Those of us that have worked in this space for quite a while are familiar that this is a real challenge. The methods are not standardized like they are, for instance, in many of the methods in oil testing or even in soybean meal testing, where the industry had to be standardized around things like protein solubility, anti-nutritional activities, et cetera, et cetera. The protein industry is crying out for this, not just with proteins, but as we've had some terrific content both today and yesterday about the interaction of proteins with other materials that would find their way into commerce together. This complicates the situation, but it also makes it real. We recognize fully at AOCS that many of these are closely guarded trade secrets, because oftentimes they form the core of intellectual property with ingredient solution providers, and that knowledge of those application contexts are very important. So some of those types of that knowledge, may not be willing. People may not be willing to share, but we hope that there will be things that are certainly pre-commercial, where standardization of a lot of these methods will go a long way in helping accelerate and advance the industry and accelerate the pace of innovation as these novel materials come forward. So I'm going to leave it at that. Please reach out to any of us at AOCS if you have interest. A number of you already have, and we thank you for your interest and your effort already. And Scott will be leading this charge, and many of us who share his passion and intent for standardization here. Thank you in advance for your interest and your willingness to participate. So with that, I'm going to turn it back over to Elaine, in hopes that we have the results of the poster pitch. Elaine, back to you.
The scores down from the chat. All right, so then now we have the drum roll, and this is the result of the judges voting as well as the audience votes. So I am very privileged to have moderated this session and to announce the winners. So the winner is H.A. Gulkirpik. Congratulations. The runner-up is Nadia Grasso, and then Anna Cäcilie Möller is the third place finisher, and they're all winners because they all were outstanding compared to the other presentations. So the first prize winner is a $300 cash prize with a recognition certificate and an AOCS student membership. There's a $200 cash prize and certificate for the second, and a $100 cash prize and recognition certificate for the third place finishers. So again, I'm so happy that you had the opportunity to present your work to this audience. I know in this pandemic time, it's very difficult for you as students to get your research recognized and out there as much as you would in other circumstances. So it was our privilege to host you guys, and congratulations. And with that, I want to remind everybody that we're going to have our third and final day tomorrow, starting at 8 a.m. Central Daylight Time. And the keynote presentation there will be Dr. David Skibby, Principal Scientist in Quality for Agronomic Traits Group at Syngenta. And he will be speaking on engineering the perfect soybean for food, feed, and global sustainability, which I think touches on a lot of the things that the students are working on too. So to our future leaders, thank you again. And I will close out. Thank you.